Good morning. Good morning, everybody. And welcome to today's lesson. Today, we're going to do a Form 4 topic.
Man, took off 6 people, man. What the hell? Well, like, took off 6
kindly
too.
mute your... So, today, the plan is we do the second last chapter of paper 1, which is uniform circular motion. I know the first chapter is thin lenses, but we normally finish with paper 1 chapters before we embark on the remaining paper 2 topics. So in Form 4, we only have 2 chapters, which are in paper 1. The first one is the uniform circular motion, and the second one is floating and sinking. So as we wait for others to join, I think because of time, they will be joining us in due course. Let us begin. So I have shared the screen on uniform circular motion, and I believe you can see it. So in this chapter, we talk about movement in a circle. So in Form 3, we did linear motion, movement in a straight line, where we talked about free fall. We talked about we also talked about projectile motion. So this time we're going to talk about movement in a circle. So in this chapter, we can see on our screen, we have a merry-go-round, we have somebody whirling. This is called whirling, W-H-I-R-L, whirl. Rotation of the stone tied to a string is what we call whirling. Then we also have a centrifuge down here. Centrifuge is a device used to separate milk and ghee. So all those describes, they describe uniform circular motion. So you have some terms that are used. The first term is called angular displacement. Remember, we have linear displacement denoted by S in Form 3, and we have angular displacement denoted by theta in Form 4. So linear displacement, we said that it's actually length between 2 points in a particular direction. But when it comes to angular displacement, then this is not length, but it's an angle. We can see it's over here, angle AOB. That is the angular displacement. And it's denoted by theta, and it's not measured in degrees. It's measured in radians. So you should be able to define angular displacement by saying that it's the angle described by a particle about the axis of rotation in a given time. Angle described by a particle about the axis of rotation in a given time. You can also define it using your own words, as long as the meaning is brought out. For example, somebody can say, this is the angle subtended at the center of a circular path when a body moves in circular motion. Angle subtended at the center of a circular path when a body moves in circular motion. So mathematically, if you want to get angle theta, then we divide displacement S by radius of that circle. So that is term number one. Angular displacement theta equals to S over R, which is the arc length over radius. So it's important that you know how to calculate angular displacement using that equation. Theta equals to the arc length divided by radius of the circle. Next, we have an example here. Not an example, but definition of a radian. A radian is defined as an angle of sector of an arc length, which is equal to the radius of the circle. Now back to this diagram here. Suppose S equals to R, then the angle here, subtended here, will be 1 radian. If AB equals to radius, therefore we will have the angle subtended here, which is angular displacement, to be 1 radian. So definition of a radian is angle of sector of an arc that is equal to the radius of the circle. So as you can see here, if S equals to R, then theta equals to 1 radian. Now, where the 360 degrees is coming from, how do we say that the circle subtends 360 degrees at the center? Let's now look at the whole circle here. A body coming from A, it revolves around and comes back to A. Then we can say that theta, which is angular displacement, will be equal to the circumference, because it's the whole revolution, divided by radius. So theta equals to 2 pi r, which is our circumference, over r. Therefore, r cancels and we remain with theta equals to 2 pi radians. So if a body revolves around the circle and comes back to the starting point, then it has covered 2 pi radians. 2 pi radians. In other words, we can say 2 pi radians are equivalent to 360 degrees. Radian is equal to 180 degrees. That is pi radian, it's 180 degrees. Then pi over 2 radians is the same as 90 degrees. Pi over 4 radians is the same as 45 degrees, and so on. So pi can be used. So you only need to understand that 2 pi radians are equivalent to 360 degrees. From there, we move to angular velocity. So remember, in the first case, we have just said that the first term is, for those who are joining now, the first term is angular displacement, and we've said that it's given by arc length over radius. The second term, term number 2, and I want us to express it in different versions. So in the second term is angular velocity. Angular velocity. It's denoted by letter omega, which is on your screen. It's a Greek letter, omega. Now, the first one, part A, angular velocity. This is the rate of change of angular displacement. You should know the definition first. Rate of change of angular displacement. So we have just said that angular displacement theta equals to s over r. Therefore, omega equals to theta over t. Omega equals to theta over t. Therefore, this omega equals to s over r divided by t, which gives us s over rt. S over rt. So remember, I'm quoting very small derivations of omega. The first one, rate of change of angular displacement. Therefore, angular velocity omega equals to theta over t. That is 1, Roman 1. Roman 2, angular displacement, angular velocity omega equals to s over rt. I've just taken s over r divided by time, and I've gotten s over rt. So that's the second way of expressing that. The third way of expressing that is omega equals to, we know from linear motion that s over t gives us velocity, linear velocity. Therefore, omega equals to V over R. That's the third way of expressing that. So we have the first way, omega equals to theta over time. Second way, omega equals to S over RT. Third way, omega equals to V over R. We still continue with the list. Let's go back here so that here we've just said that when the revolution is expressed in terms of angular displacement, then the whole revolution will be 2 pi over t. I mean, 2 pi radians. Therefore, the fourth way of expressing this is angular velocity equals to 2 pi radians divided by total time, capital T. Capital T is the time taken for one complete revolution. So distance for one complete revolution will be 2 pi. And then the total time for one complete revolution will be capital T. So we can also express angular velocity as omega equals to 2 pi radians over T. That's formula number 4. Formula number 5. We know that from waves, periodic time T equals to 1 over F. So when we substitute in equation number 4, then we get omega equals to 2 pi over 1 over F, which simplifies to 2 pi over, 2 pi F. So 2 pi F is another way of expressing angular velocity, which is formula number 5. So this omega can be expressed in so many ways. 1, theta over t. Omega equals to theta over t. Number 2, S over RT. Number 3, omega equals to V over R. Number 4, omega equals to 2 pi over t, periodic time. Number 5, omega equals to 2 pi f. So depending on the question, you will be able to choose which one is the best or which one is applicable. So here, they've just shown the derivation from what we just said to obtain that omega equals to V over R is the same. Omega equals to 2 pi over t is the same, or omega equals to 2 pi f, same derivation. So we have a question here. Example number 1. It says a turntable rotates at the rate of 45 revolutions per minute. What is its angular velocity? So 45 revolutions per minute is actually the frequency, but we need to express it in revolutions per second. So 45 revolutions take 60 seconds. So how many revolutions will be in 1 second, so that we get the exact frequency? So we'll have 1 over 60 times 45. And that gives us 0.75 Hz. 0.75 Hz is our frequency. Then, among the among the 5 equations, which one is suitable? Is the one that says omega equals to 2 pi f. So when you substitute, you have 2 times pi times 0.75. So using the calculator, the answer is 4.712 radians per second. 4.712 radians per second. So when you see the word revolutions per minute or revolutions per second, it simply guides you towards frequency of that motion. Number 2, we have the first question A that says, a model car moves around a circular track of radius 0.4 meters at 2 revolutions per second. Remember, I've just said that 2 revolutions per second gives us a frequency. What is its angular velocity? So you will come and say that angular velocity omega equals to 2 pi f. Substituting, we have 2 multiplied by pi multiplied by frequency, which is 2. Because we are told 2 revolutions per second. That's the same as saying 2 hertz. So 2 times pi times 2. The answer is 12.57 radians per second. 12.57 radians per second. And then Roman, I think that should be the answer to, they forgot to write Roman 1, which was asking for angular velocity. We've just done it, 12.57 radians per second. Then the second one is the speed v. So from the 5 equations, you look for the equation that has v, and it's the one that says omega equals to v over r. And we have our omega is 12.57 equals to v, which we are looking for, divided by radius, which is given as 0.4. Therefore, the answer would be 5.027 meters per second. So that's the linear velocity v, 5.027 meters per second. Part B says, find the angular velocity and the frequency of the motion of the car if it moves with a uniform speed of 2 meters per second in a circle of radius 0.2 meters. So let's start with the angular velocity. Omega equals to v over r, v over r. So substituting, v is 2, radius is 0.2. Therefore, we get 10 radians per second. Angular velocity is measured in radians per second, written as rad per second. Then the second part says find the frequency. So you will say omega equals to 2 pi f, and we're looking for f. Therefore, f will be omega over 2 pi. So we have 10 divided by 2 pi. So 10 divided by 2 pi gives us 1.592 hertz. 1.592 hertz is the frequency of that revolution. So these are some of the questions that come from angular displacement and angular velocity. So let's move to centripetal acceleration. Centripetal acceleration. So just like linear motion, we have acceleration A. In uniform circular motion, we also have acceleration A. So if you're asked to define, just say that this is the rate of change of angular velocity. Rate of change of angular velocity. That's the simple way of defining centripetal acceleration A. Rate of change of angular velocity. Now, one thing you should note that if we have a body like this one, let's use this diagram here. A body that is revolving around this circle does not change linear velocity. The velocity, linear velocity V, remains the same at A, it will be the same at B, is the same elsewhere on the circle. Does not change. If it's rotating at 20 meters per second, it retains the 20 meters per second unless external force acts on it. But then why do we say that it's accelerating? It's accelerating because of change of direction. Just by changing direction, that's continuous change in direction, because the direction it's moving at A is not the same direction in which it's moving at B. They are different. So since there is the change in direction, therefore, and we know that velocity is a vector quantity, we say that there is a change in velocity, even if the magnitude is the same. That's why here we say that a body in circular motion is accelerating. So the most commonly asked question here is that explain why a body in circular motion is said to be accelerating, even if it's moving with a constant linear velocity. Then you should respond by saying that the body keeps on changing direction, hence changing the velocity, which is, of course, a vector quantity. Now, that acceleration A is given by V squared over R. So acceleration in a circle equals to V squared over R. So that is one way of expressing centripetal acceleration. The second way of expressing it is we are going to substitute the formula that we've just learned, that omega equals to V over R. Therefore, V can be written as omega R. So substituting in this equation, we get acceleration A equals to omega R squared. Remember, V is squared. Therefore, omega R squared over R. So simplifying, we have acceleration equals to omega squared R squared over R. Therefore, acceleration A equals to omega squared R. So the second formula for centripetal acceleration is given by omega squared r. So we have two of them, v squared over r and r omega squared. We have a question here. A point on the rim of a wheel has a velocity of 5.6 meters per second. If the rim has a radius of 0.4, I think it's 0.4 meters, calculate A, the angular velocity of the point. So of course we have 5 formulas for angular velocity. So we choose one. We can say that omega equals to v over r. Because we have velocity, we also have radius. Therefore, omega equals to 5.6 over 0.4, which gives us 14 radians per second. And then centripetal acceleration. B is centripetal acceleration. So say acceleration A equals to v squared over r. Our v is 5.6 squared. R is 0.4. So 5.6 squared divided by 0.4 gives us 78.4 meters per second squared. The units of acceleration are the same, meters per second squared. Then there is another alternative down here, which says acceleration equals to r omega squared. So when you substitute, you get the answer, the same answer, 78.4. Another example, a body having a mass of 0.5 kilograms is tied to a string and whirled in a horizontal circle of radius 2 meters with a speed of 3.16 meters per second. Calculate A, the centripetal acceleration. So here we have the speed and we also have radius. So write part A, acceleration A is v squared over r. So substitution, we have 3.16 squared divided by radius 2. So 3.16 squared divided by 2 gives us 4.993 meters per second squared. 4.993 meters per second squared is the answer. And then part B, we need to talk about the centripetal force first. So you are supposed to know how to calculate centripetal force. So whenever we have a body that is revolving in a circle or moving in a circular motion, whether it's on a flat surface, let's say a car revolving around the roundabout or merry-go-round, then it experiences centripetal force. The centripetal force is the one that keeps it moving in that circle. If it's not there, then the body will not be able to move in that circular path. So it actually pushes it towards the center of the circle. So on the screen here, we have a body describing a circular orbit. We can see where the centripetal force is pointing towards the center. So this is the force required to keep a body moving in a circular path and is directed towards the center of the path. So if you're asked to show the direction of the force, is always towards the center. The opposite of this is centrifugal, which is not taught in this chapter, but we only mention it. This force actually is provided for. What do I mean by it's provided for? Like in this case, this is probably a stone tied on a string. So the string experiences tension force towards the center. So the force that provides for centripetal force is tension force in this particular case. If we have a vehicle moving around about, then that force is provided for by the force of friction between the tires and the road. I think those are the main cases. So we have tension force providing for centripetal force. We can have friction force providing for the centripetal force. So you will find some books even saying that centripetal force literally doesn't exist. But you should understand that it's a force which is provided for by other forces, e.g. tension and friction. Now, from Newton's second law of motion, Form 3, we said that F equals to ma. Force, the resultant force F equals to mass times acceleration. And we have already known that acceleration can be written in two ways. It can be written as A equals to V squared over R, or it can be written as A equals to omega squared R. Therefore, substituting here, both of them separately, we have the first equation will become A equals to F equals to M V squared over R. F equals to M V squared over R. And the second version will be F equals to M omega squared R. M omega squared R. So that is how we can be able to express the centripetal force F. So centripetal force is written, sometimes you will see books writing capital F subscript C equals to mv squared over R, or capital F subscript C equals to M omega squared R. So here we have question part B, which says, calculate the tension in the string. So that tension is the one that is providing for centripetal force. So we will come back and solve that question. Factors affecting centripetal force. From the equation that we've just written, we have written F equals to M omega squared R. Those are the factors affecting centripetal force. M omega squared R. So number one is the mass of an object. And we've been told that the heavier the object, the more the centripetal force it needs to maintain it in that particular circular path. You have seen people getting it very difficult to negotiate around a bend. Maybe a bus coming very fast, and then the driver is not able to negotiate that bend. Then he finds himself out of the road, causing an accident. So what happens is that this bus is very heavy. So it requires him more centripetal force, which will be the friction force between the tires and the road, to keep him negotiating around that bend. But a small car coming at the same position with the same velocity, it will be able to pass, because this person needs a very small centripetal force to negotiate that bend. Factor number 2, angular velocity of the object, omega. An increase in angular velocity causes an increase in centripetal force needed to maintain the object in the circular path. So from what I've just explained is that if this bus driver came to that point at a slow rate, because remember, angular velocity depends on linear velocity. Suppose he was moving at a lower velocity, then he will be able to pass without any problem. But because the velocity was very high, which also increases angular velocity, then he skids out of the road. That's why you will see that some corners on the roads have maximum speed limits. So you're not supposed to supersede that speed. Factor number 3 is radius of the path. So for mass, we've said increase in mass results to increase in centripetal force needed. Increase in angular velocity results to increase in centripetal force needed. And when it comes to radius, is the opposite. Increase in radius leads to decrease in centripetal force required, and vice versa. Because if we have a large roundabout, then somebody can pass there with a very high speed without any problem. But if a roundabout is very small, then you cannot pass there at a high speed and a larger, heavier vehicle. So as we can see from the formula, F equals to mv squared over r. Radius is inversely proportional to the force required. Sometimes people wonder, why do we have, you see a bus causing an accident on a very flat surface? It's because of some of these factors: mass, angular velocity, and radius of that bend. Examples of circular motion. So examples of circular motion, we have the first one. When we have a car rounding a level circular bend, that's an example of circular motion. We can see this vehicle in a corner here. The circular bend is on the right, the driver's right, and he needs a very high frictional force to be able to pass and negotiate that bend. So centripetal force required for a circular motion is provided for friction force, by frictional force between the tires and the road. So friction force is equal to mv squared over r. I think we know where mv squared over r is coming from. If the road is slippery, then the frictional force will not be sufficient to provide the centripetal force. Therefore, this driver is going to skid. So to prevent skidding, the car should not exceed what we call the critical speed. So that brings us to another question that's always asked. Define critical speed as used in uniform circular motion. Define critical speed as used in uniform circular motion. So you say that this is the maximum speed. This is the maximum speed beyond which a vehicle skids when moving in a circle. Maximum speed beyond which the vehicle skids when moving in a circle. To also assist in preventing skidding, we have roads that are banked, banking of roads. So here we have a road that is raised on one side. As you can see, on the right is raised and on the left is actually lower, forming a dome shape, D-O-M-E, dome shape. So in this case, if we raise the road like this on one side and somebody is passing there at a higher speed, then we reduce the chances of him skidding. So define banking as used in uniform circular motion. To say this is raising of one side of the road from the inner side to prevent skidding of vehicles. Raising of one side of the road from the inner side to prevent skidding of vehicles. So the forces acting on the vehicle as it passes through that point are shown on the car here. We have the one that points towards the center of the bend, which is N sine theta. We have another one that points down, which is the weight given by mg. Then we have another one that points up, which is the reaction force. Reaction force, remember, is supposed to be equal to the mass, to the weight, but you can see it's bending there, N. So we do what we call resolution of forces. And then we get N cos theta. So vertical component is N cos theta. Horizontal component, which is centripetal force, is N sine theta. And weight is mg. So this should not scare you. They are just representing the horizontal component to the center of the circle is centripetal force, which of course is the same as friction. Vertical component up here is the reaction force, which is N cos theta. Then down is weight. Now, we've been told that N sine theta is centripetal force, N cos theta is weight of the vehicle. Therefore, when we divide Roman 1, okay, Roman 1 here, we are told that centripetal force equals to mv squared over r, which we know. I think we understand that Fc is mv squared over r, and weight is given by mg. In maths, tan theta equals to sine theta over cos theta. I think we've done trigonometry 2. in mathematics. And if we have not done, we just borrow a little from there. Tangent of an angle is equal to sine of that angle over cos of that angle. So let's understand that. Therefore, when we divide now n sine theta over n cos theta, which gives us now tan theta, we get mv squared over r divided by mg. mv squared over r divided by mg. And we now make v the subject of the formula because we are interested in what is the speed beyond which that particular speed the car is going to swerve around or skid around. So we make v the subject of the formula, and I'm sure you have also done formula and variation. You have also done how to make subject of the formula. So v squared equals to rg tan theta. Square root both sides, then we get v equals to rg tan theta square root under square root. So that v gives us the maximum speed required for a body moving in a circular path whose angle of banking is theta to prevent skidding. So if the speed is written 30, the traffic sign written 30, then you're not supposed to go beyond 30 because it has been calculated using radius of that bend times 10 times the tangent of banking of that angle, then square root. Now, before I welcome questions, this is the critical angle for a banked road. We've also talked about the critical angle here on a flat surface. Remember, this road has not been banked. So if it's on a flat surface, for us to get the critical angle, then we are going to have, we know that velocity, acceleration A equals to v squared over r, and v therefore equals to r times a. V squared equals to ra, and therefore v is the root of ar. So if it's a flat surface, not banked, then we find critical speed by multiplying acceleration times radius of that place under the root sign. So far, I think we can welcome a few questions on banking of the road, and also the previous work we've done about angular velocity, angular acceleration, centripetal force. So if you have a question, hands up. Okay. I think we have a question from Victor. Go on. Victor, I can't hear you. Check your microphone. Victor? Okay, let's listen to Alvin Ongombe. Alvin? Patrick?
I wanted to ask, for example,
Yes.
since you said that the centripetal force is the one that keeps the object in the in the path around whatever it's rotating, does that mean so gravity is a form of centripetal force?
No. Gravity only comes in when we are having a body. You know, we are going to learn about vertical motion. We have actually two types of circular motion, uniform circular motion. We have movement in a vertical circle, like a roundabout, a merry-go-round. And we have movement on a flat surface when a vehicle goes around a roundabout. So those are two examples of one is vertical, the other one is horizontal. So where we are bringing in the gravity issue for us to get the critical speed on a banked road is where we have the root of RG tan theta. So G is coming in because we have raised this road from the flat surface upwards. That's we have the gravity coming in.
Okay.
Otherwise, if it's on a flat surface, then G is not supposed to be part of it.
Okay, thank you.
So I hope it's clear. Yeah. We have somebody who is raising it. Okay, we can proceed. Then we will be able to attend to questions in due course. Now, this is for a banked road. I've explained critical speed is the root of RG tan theta. Now, we've been told here that this critical speed of a car in circular motion depends on these factors. Actually, the factors are written there in the equation. Remember, G is constant. Therefore, number one is radius of the bend. Number two is the angle of banking. We can see tan theta. And then number three, the condition of tires and nature of the road surface. So you can see the weight here has not been factored in. So it's not a factor. It's the condition of tires and nature of the road, radius of the bend, and angle of banking. Those are the three factors affecting critical speed. Case number two. We have seen cyclists during Olympics. We have seen even other circuits organized by different countries. Here in Africa, that sport has not been very well developed, but these people experience also centripetal force. We also have bicycles at home, and at a point, probably you have fallen a victim of a small accident. So as this person rotates around the bend, what are the forces acting on him? There are three. One, we have centripetal force. Centripetal force, mv squared over r here. We have frictional force. Frictional force is the same force providing for centripetal force. So this force and these are actually the same. That's why it's not skidding. Then three, we have the weight of the bike plus the rider. So this one acts like a a body which is in equilibrium, where we have the pivot and we have the moments. So here we take moments about C. Where is C? C is over here. That's the position where we take the moments. So clockwise moments are equal to anti-clockwise moments. So we have this reaction force R, which is the same as weight. So R multiplied by perpendicular distance. Perpendicular distance from this line to C, this point, is given as X. I think you can see X written down here. R times X, that is the clockwise moment, equals to anti-clockwise moment, which is friction, this one, multiplied by Y. Y is from down here all the way to C. So Rx equals to friction times Y. So when we express X over Y, we get friction over R. And then we know that R is given by mg, reaction force equals to mg, which is weight, and friction force equals to the centripetal force, which is mv squared over R. So dividing friction over R, mv squared over R divided by mg, we get this one. So mass cancels. Then there is an angle here at which this person is bending, here, theta. Tan theta equals to opposite over adjacent. So opposite is V squared. Remember here we have remained with V squared, and adjacent is RG down here when we cancel M. So tan theta is V squared over RG. Therefore, V still gives us RG tan theta, just like for the car. So this is the critical speed. Now friction, we know from Form 3 that friction is the coefficient of friction times mg or R. Mg tan theta equals to coefficient of friction times R, which is mg. Therefore, tan theta equals to the coefficient of friction. So the tangent of this angle here gives us the coefficient of friction of this surface. So this is just additional information, but we have seen the critical speed over here. If this person exceeds this speed, then he's going to skid or get out of the road. So that's another way of circular motion. Maybe not really seen questions from this area, but this equation, you should be aware of it. You can be asked to calculate the critical speed or define it. Another area of uniform circular motion is the aircraft banking, where we have an aircraft that is making a turn. Those who take aviation, I think, understand this more. The aircraft must roll to a banked position so that its wings are angled towards the desired direction of the turn. So the aircraft cannot turn when it is horizontal. It has to incline at an angle theta. And also the speed at which it's moving should also obey critical speed. V equals to the root of RG tan, this theta here. Conical pendulum. A conical pendulum is simply a bob tied on a string, then being whirled in a vertical, horizontal circle like that, but tied vertically up here. So it makes something like a cone as it's being whirled around here. Forces acting on this, we have the tension force up here, centripetal force, T sine theta. Then we have weight down here. The vertical component is T cos theta. Now, here, for it to obey that critical speed thing, then tan theta, theta is up here, I think we can see it, equals to V squared over RG, where V is the linear motion, linear velocity with which it's moving. So this conical pendulum is used in speed governance of a vehicle. It's designed in a way that when the speed of rotation increases, we have two types of speed governors, a manual one, which is this one, and we have an electric one. Most vehicles have an electric speed governor. This one is a manual one, where it's connected to the shaft like those heavy commercial lorries. So the more the shaft rotates, the speed increases, then this bob is going to rotate very fast, and the angle theta here increases because this one will have a lift. It's lifted up. And in that process of lifting it up, because it's very fast, it disconnects the fuel supply to the combustion chamber. So since the fuel is cut, then it cannot go beyond a certain speed. So this is another application of uniform circular motion. Not application, but a case study of uniform circular motion. Now, movement in a vertical path. Remember I talked about merry-go-round. When we have people revolving in that manner, then they are moving in a vertical path. So it's good that you understand that the force that provides centripetal force towards the center is tension in this, whether it's a rope or a string or a piece of wire or a metal, it experiences tension towards the center. So down here, when the person is down here, he experiences a downward force, which is weight, and an upward force, which is tension towards the center. So the total tension here, down here, is given by T equals to mv squared plus mg. Up here, which is the opposite part, you can see the direction of forces. Weight down, tension down. So the net tension in the string will be mv squared over r minus mg. On the sides, C and D, we can see mg down both sides, but tension towards the center. So this mg does not affect the net tension in the string. So we have mv squared over r here, mv squared over r here. So at the end of the day, when we compare all of them, we find that tension in the string at the position B is the highest here. So when the body is here, the rope experiences the highest tension. And that's the point where it can easily cut. And this, whether it's a person or a stone, is going to leave the circular motion. Followed by C and D, because they are not being affected by the acceleration due to gravity. At C and D, tension is not affected by acceleration due to gravity. And the last tension is at A. This is the least. And at this point, you can see mv squared over r minus mg. So this one experiences the least tension. Now, at point A is where we have the rope. The rope can become loose. In other words, it may not be straight tight or taut. We have to revolve it in a certain minimum velocity. So anything that is lower than that velocity, then the stone is going to collapse. It must remain taut here. So to calculate that velocity, just like what we did here for the flat rod, is V equals to the root of RG. So velocity for the rope to remain taut at point A is given by V equals to square root of RG. So many questions can come from here. A stone is whirled in a vertical circle. State the position at which the rope is likely to snap. Then you say it is at the bottommost part. Give reason. This is the position where it experiences the rope experiences the highest tension. Another question. Calculate the minimum velocity at point A for the rope to remain taut. Then you say V equals to the root of RG. Then the answer you get is the minimum velocity. Then 3, you will be asked calculate tension at any point, maybe A, B, or C, D. So you need to know that here we add down here we minus, and these ones we don't add. We neither add nor minus the mg weight. So this one now takes us back to this question that we never completed. Part B, I think it was prematurely set. We have a question here. This one. A body having a mass of 0.5 kilograms is tied to a string and whirled in a horizontal circle of radius 2 meters with a speed of this one. Calculate the tension in the string. When we have a horizontal circle, we don't involve mg, which has been done here. I don't know what this one is, but you simply say tension T equals to mv squared over r. So mass times velocity squared, that is 0.5 times 3.16 squared divided by 2. So from the calculator, 0.5 times 3.16 squared gives us 4.993 divided by 2. The answer is 2.496 newtons. So it's just simply tension equals to mv squared over r, because it's tension that provides for centripetal force. So back here on vertical motion, somebody could be asked